What are nonlinear dynamics in control systems? Imagine a system that doesn't follow a straight line when you change its input. Instead, it behaves in unpredictable ways, sometimes jumping or oscillating. That's what nonlinear dynamics are all about. In control systems, these behaviors happen when the output isn't directly proportional to the input. Unlike simple systems that follow predictable rules, nonlinear systems can have multiple equilibrium points, meaning they can settle at different states depending on initial conditions. They can also show limit cycles, which are repetitive oscillations or even chaos, where tiny changes in starting points lead to wildly different outcomes. In electrical engineering, nonlinear dynamics show up when the relationship between variables involves nonlinear functions. For example, when a magnetic core in a motor reaches saturation, the magnetic field stops increasing proportionally with current. This saturation is a nonlinear effect. Other examples include friction in mechanical parts or saturation in electronic components like transistors. These effects make the system's behavior more complex and harder to predict with simple equations. Because of this complexity, traditional linear control methods don't work well with nonlinear systems. Instead, engineers use special techniques like feedback linearization, which simplifies the system by canceling out nonlinear parts, or sliding mode control, which forces the system to follow a desired path despite nonlinearities. Backstepping and Lyapunov-based methods are also common, helping to design controllers that keep the system stable even when it behaves unpredictably. In feedback control, nonlinear dynamics are important because the system's response to inputs and disturbances can change dramatically. Small changes can cause big effects, making control more challenging. Engineers need advanced mathematical tools and computer simulations to understand and manage these systems. In practical electrical engineering, nonlinear dynamics matter in power electronics, where inverters must keep a steady sinusoidal output even when loads change suddenly. Motor drives also face nonlinear effects like magnetic saturation and friction, which requiring specialized control strategies to keep performance high. Robotics and aerospace systems often involve complex mechanical and aerodynamic interactions that are inherently nonlinear, making control design more demanding but also more interesting. To sum up, nonlinear dynamics in control systems describe behaviors that are not straightforward or proportional. They are common in real-world electrical systems, and managing them requires advanced control techniques to ensure stability and good performance across different operating conditions.